I forget what I said. I wrote this though, so that's good.
Yeah.
Okay. Now transit. There's there's a third one, right? Transitivity, or as is popular to say these days, trans. Let's see here. Oh no. I mean, oh yes. I don't know. What are we supposed to say here? I'm not sure. God loves everybody. Yes, I believe that's the word to say. Right. F equivalent to G, G equivalent to F, H rather. We'd like to show what?
Equivalent to H.
Right. So let's suppose that F is a proof that F is equivalent to G, and let's suppose that G proves that G is homotopic to H. We need to construct H. Let's see here. We want H of x comma t equal to.
P squares, right?
What's that?
Yeah, P squares. So it's
Yeah.
f of x 2t.
1 minus 2t?
Uh,
0 less than or equal to t less than or equal to 1/2. 1/2. Is that it?
No, I don't
No, that
think
can't
so.
be it, because that's going to be -1.
It's going to be 1/2. No.
2t minus 1?
Yeah, I think it's 2t minus 1. Yeah.
Yeah, that.
Sweet. I think that's sweet. Let's see, does it work? It's definitely continuous on both pieces, right? How about what's the overlap of these closed sets whose union forms the unit interval from 0 to 1?
F of x1, which is g of x, which is also big G of x0, which works.
Right, because this is what?
Little g of x.
Okay. And you notice what we're doing here is we've got 0, 1/2, union 1/2, 1 is equal to 0, 1. So by the gluing lemma, the fact that this is continuous and that's continuous means that it's continuous. That's where the gluing lemma is used. Although I probably would have believed that without the gluing lemma, but it is comforting. Yeah. Is good. All right, so this allows us to define, homotopy classes, right? So let me just read ahead a little bit without writing anything. We'll write these things down next time anyway, but just since we have a minute. F from x to y continuous, the homotopy class is the equivalence class of all functions which are homotopic to f, right? And you can look at the family of all such homotopy classes. He then proves something nice as it relates to composition. And basically the point is that homotopy is a congruence on the category of top. So it sort of lumps different things which would be different topologically together as one thing in homotopy. So homotopy loses some topological information, right? But it's still useful. I mean, at the minimum, if you can prove that two spaces aren't homotopic, then they're not homeomorphic either, right? So the quotient category just described is called the homotopy category, and it's denoted by h-top. All the functors, t top to a, we shall construct where a is some algebraic category, groups, abelian groups, rings, will have the property that f homotopic to G implies that the functor of T, the functor acting on F is equal to the functor acting on G. So, in other words, our functors play nice with the homotopy that we're discussing next time. So anyway, next time hopefully we'll talk about homotopy, convexity, contractibility, cones perhaps. We'll see where we get to. I will do my best to say something meaningful. As you know, I have a certain mental stumbling block when it comes to cones. You may recall advanced calculus, so hopefully I'm past that, whatever that was.
Oh, the geodesics of a cone?
No, just the things he said about, there's a problem on cones
that's right, yeah.
in Rentland I couldn't make sense of, and I don't know. Well, anyway, I find that when I read this book, it makes sense to me, if I have time to actually read it. And so anyway, we'll stop here. Thanks, guys.
We should have more of that next class.